All right, grade 12s, we're now going to look at chemical change, part 1. We're looking at module 5 on page 249, and we're looking at acids and bases. Now, the first thing you'll see if you've got the notes in front of you is that unit 11, which is acids and bases just general, is a revision of grade 11 work. You do need to go through it. So this is the different properties. They taste bitter or sour and those sort of things. Please, you need to work through that. And then you need to work through activity 1 on page 251, questions 1 to 4. The answers will be on teams. Then we look at acid-base reactions for the next part. Now, you've done this a lot. This is stuff you've done since you were in grade 9. You spent a lot of time on this in grade 9. We did it again in grade 10. You did it again in grade 11. So you need to work through those again as well. Please make sure you do activity 2 on page 253. The answers are on teams. Unit 13 is also revision with conjugate acids and bases. Okay, make sure you work through that again on your own. This wasn't done with anyone in class. We just did the activities. So now you also need to do activity 1 on page 255 and activity 2 on page 257. If you need to do those now, work through those first. Pause the video, come back to it once you have completed those. Let's go to unit 14. So here we're starting something new. We're going to look at strong and weak acids and bases and how we define them. So starting with acids, a strong acid ionizes completely in water to form a high concentration of H3O plus ions. Acids are always covalently bonded. So what actually happens is they physically react with the water and that creates our ions. Okay, so what happens here is we have HCl reacting with the water, forces us to get H3O plus and Cl minus. The first arrow is much longer because it shows me that I get a lot of product by the time I get to the end and very little reactant. Okay, so we assume for strong acids that we have complete ionization, that it all goes to ions, but in reality they don't, okay, because it's an equilibrium system. Now we have a list of strong acids. You must learn this list, okay? You must know these. If you get given an acid and it doesn't fit one of these 6, then it's a weak acid, okay? They're not going to ask you to identify an acid you've never seen before as strong or weak if you haven't done a pH calculation, for example. It's all stuff you need to get from here, okay? Now, a weak acid only ionizes a little bit. So it doesn't dissolve well in water, but it's the same process. The H is going to come off here. The H is going to be given to the H2O. That results in the H3O plus ions and the acetate ion in this case, which is the negative. Here, I've got the back arrow, the reverse reaction being longer, because I have a lot of product when I get to the end, okay, I have a lot of reactant and less product, okay. So acids ionize. They always ionize because they are covalently bonded. When we look at bases, now bases it's not all bases. Bases have their own little way of doing things, okay. So a base now, a strong base, dissociates. Strong bases are ionic. So they are made up of positive and negative ions. Those ions can be forced to move away from each other. So we have sodium hydroxide, which becomes a lot of the sodium becomes Na plus and OH minus. Okay, so we say we get lots of these. And in fact, this ion there, the H3O plus, this is what makes it acidic. That's the one that's dangerous. This ion in a base is what makes a base dangerous. They're very reactive ions, okay? And they like to react. When I have okay, first of all, before I get to weak base, here I need you to see something. This is our list of strong bases. All of these metals, these are your group 1 metals. When they bond to OH, they become strong bases. If you get given a base that doesn't fit into this list of 6, it's a weak base, okay? Weak bases work a little bit differently now. Now I say they can dissociate or ionize because this example, ammonia is a weak base, okay? But it's not ionic, it's covalent. So it can't dissociate, it has to ionize, but it only ionizes a little bit, which is why we get a long arrow to the left. What's going to happen here is the H2O is going to give a high H plus ion to the ammonia to form ammonium. What are we always forming though? The OH minus ions. Strong acids, we get lots of ions. Strong bases, we get lots of ions, lots of product. Weak acids, we get very little product, lots of reactant. Weak bases, very little product, lots of reactant. Okay? Please, you now need to do activity 1 on page 259, and then you can move on. Last part of this section is concentrated and dilute acids. Now here you got to get the difference between strong and concentrated. They are not the same. A concentrated acid or a base contains a large number of moles of the acid or base in proportion to the volume of water. So it means we have a lot of acid in whatever volume of water we have or base. Dilute means we have very few of those particular particles that make it an acid or a base. So if we look here, this is a picture of a dilute solution of the strong acid HCl. It's dilute, but it's still strong. Here I have a concentrated solution, lots of HCl particles, but now it's still strong. The difference here is the concentrated will just react faster. Rates of reaction, okay? But whether it's concentrated or dilute, it's still a strong acid. If I look at ethanoic acid, this of course is vinegar. Vinegar is a weak acid. Okay, so both of these are weak acids. Both of them. All right. As a weak acid, you can either have it dilute, like the vinegar you use on your food, all right, or it can be concentrated. That's hideous to smell. It burns your nose, all right? But both times, they're still weak acids. This one just is going to react slower because it's dilute. This one's going to react faster because it's concentrated. So how do we dilute an acid? Well, we have a very interesting equation, which is this. When I dilute an acid or a base, okay, so basically what happens here is we have our original solution, and here I have my particles, and then I add more water into it. I'm not adding more of the particles, I'm just making the volume different, which means the number of moles stays the same. We know that concentration is number of moles over volume. So if number of moles is concentration times volume, number of moles stays the same. So whether I have the original concentration of volume or I have the second concentration of volume, the number of moles in both of those solutions is the same. So it's nice and straightforward. The nice thing here is my volume can be measured in anything, okay? My volume does not need to be measured in decimeters cubed or centimeters cubed. It actually doesn't matter, all right? The volume, because the volume cancels each other out. You just want to make sure it's the same. Then, of course, you need to remember from last year that concentration is mass given over molar mass times volume. Concentration, mass of the sample in grams, molar mass, which you get off the periodic table, and volume, which now must be in decimeters cubed, okay? So sometimes with these questions, you may need to work out the concentration before you can put it into that equation, okay? So at this juncture, you need to do activity 2 on page 260. Once you have done that, you can move on to the next video.